here's our last section. I wish it was 2 weeks ago. And we'd have 2 more weeks to review, but we have only what we have. Let's get through this. I'm going to be taking portions of this lecture out on the fly, as we're going to be short on time, and because I have to hit at least the sections, the topics in here that are most likely to show up in the AP exam. If we had another 2 weeks, we'd be able to take a leisurely walk through this, but we don't. So here we go, polar functions. Now, how many of you got an introduction to polar coordinates in your pre-calculus class? Lantern, no?
I don't remember.
I think like for a day.
For a day. All right, well, let's hit the high points then. So in our normal coordinate system, it's called the rectangular coordinate system, or sometimes called the Cartesian coordinate system. Every single point in the plane is signified by 2 points, an x value and a y value. In the polar coordinate system, we're still using 2 points to describe any points on the plane, but it's not how many over and how many up, but rather it's a description of a rotation, an angle, which we'll call theta, and theta is measured from the positive x-axis, and a distance from the origin, r. So we'll describe every point in the polar coordinate system by a value r and a value theta. This particular point, we had to rotate 45 degrees, or pi over 4 radians, to get into the right alignment. Then we moved to root 2, a distance r. So we'll call this point in polar coordinates 2 root 2, comma, pi over 4. And every point in the plane can be named using this convention. These 2 points, actually remember these 2 points, the rectangular 2.2 and the polar 2 root 2 comma point, or pi over 4, actually represent the same point in space. Yes? Yes?
So is it's basically like saying, is it all saying that x is like the cosine value at all?
Well, we're going to find out later that if I want to take this point and translate it into the old rectangular system, indeed, we're going to have a conversion. And that conversion is x is equal to r cosine theta, and y is equal to r sine theta. We'll have a slide that says that later. Why don't we do it right now since we have the ability? So here is an r, 2 root 2. Here is a theta, pi over 4. Okay, and what is cosine of pi over 4? Last time I checked, it's root 2 over 2. And if I cancel those 2's and I multiply root 2 times root 2, I get the value 2. Similarly, if I did with the y description, 2 root 2 times the sine of pi over 4, you're going to get the same thing, and we'll go and find the y value is 2 as well. So there is a sine-cosine relationship. Right? All right. Now, one of the things that's different about polar coordinates is that you can actually represent the same point multiple ways. Like we talked about this particular point, saying I rotated pi over 4, and then I went up to root 2. But there's also the idea that we can start, again on the positive x-axis, and rotate negative 3 pi over 4. And the r values don't have to be positive. we can actually start here and move in a negative direction. This same point, these 2 points are exactly the same. This point could be described as, in polar coordinates, root 2 over 2 pi over 4. But it could also be described as negative 2 root 2, comma, negative 3 pi over 4. These 2 points are absolutely equivalent. Hey, that doesn't, and there's even more than that for this point that we would have called rectangular 2 comma 2. How about we rotate starting here and go all the way around? What angle measurement is that? Starting here and going 75% of the way around the circle. I think that would be something like 7 pi over 8. And then we moved to root 2. That coordinate describes exactly the same places as the other 2 coordinates. There is an infinite number of ways to describe the same point in polar coordinates. Alrighty, moving on. Let's just do a couple of these. We won't do them all. Here are these are polar coordinates. We'd like to find the value of the corresponding rectangular coordinates. Let's draw this one out. It says rotate pi over 2. So I'm going to rotate, so I'm looking perfectly vertical up. And I go up 4. Hey, in rectangular coordinates, this would be 0, 4. Do you want to use that other function for that as well? What is that? X is equal to r cosine theta. In this case, r is 4. And cosine of pi over 2 is 0. 4 times 0, okay? Oh, 0, 0. Très bien. How about y? Y is r sine theta. R is 4. Sine of pi over 2 is 1. 4 times 1 is? 1. Oh, it's 4. Oh, 4. By hook or crook, we find the same answer. So you can either draw it out and hopefully find something nice, or use those formulas. Either way is fine with me. Love to do the rest of these, but we're short on time. May I go on to the next slide? Great. By the way, these are in the book, and there are explanations of how to do the rest of them are in the book as well. Feel free to look at them. Okay, now, how about this working the other way? What if we have rectangular coordinates and we want to convert to polars? We could take this easy one, over 1, up 0. How might you describe this in polar coordinates? How far do I rotate? 0. So my theta is 0. How far did I move from the origin? 1. Oh, so the rectangular coordinate 0, 1 has a polar coordinate of 0 and 1 as well. Let's do one more. How about negative 3, 3? So back 3, up 3. So there's our point. How far do I have to rotate around to get to that point? Hmm? 3 pi over 4 I hear, and that is correct for the angle. How far did I have to go to get out there? Well, this side of the triangle is 3. This side of the triangle is 3. This is a hypotenuse, so it's the square root of 3 squared plus 3 squared. 18, the square root of 18, or 3 root 2. Okay, that is one representation of the polar coordinates for that point. Remember, there are an infinite number of representations. Lemon drops?
Yes.
Dumbledore likes lemon drops.
Do you want one?
Just thought I'd throw that out.
I thought there were acid pops.
No, but in book 1, he tries to share a lemon drop with Professor McGonagall. Book 1, chapter 1. Okay, now, one of the things that we do in the Cartesian plane is we draw curves. We can do the same in the polar plane. In fact, in the polar coordinate system, perhaps some things are easier to describe than they are in the Cartesian plane. Let's think about the set of all points that satisfy that equation. Where are all the points that are exactly 2 away from the origin? A circle with radius 2. Where's the theta in here? Right? Huh? There is no theta. So what does that mean in this equation? That theta is allowed to take whatever value, no matter what value theta has, it doesn't break the equation. It's kind of like the equivalent to the expression, hey, I want the equation, I want to see the curve y equals 2. Hey, y is equal to 2. Well, where's the x? There is no x. So no matter where you are, there's no x to break the equation. It's true for all x. This is true for all theta, whether that theta be at 0, at pi over 2, at pi, so on and so forth. Okay, let's take a look at the second one. What is the set of all points? R is equal to -2. It would be the same thing. You're telling me that this point right there satisfies the equation R is equal to -2? Sure, when theta is equal to 0, I rotate 0 and I back up 2. Oh, right there. How about that point right there? How does that satisfy it? If the theta is negative pi over 2, meaning I rotated around this way and I backed up 2. So indeed, that point would satisfy that equation. It's kind of a weird thing. Think you're a negative R value? But mathematicians are weird. Okay, what about theta equaling pi over 6? The set of all points that satisfy that equation. Now, there's no R in here. What does that mean for our poor little R? It's just a straight line, Miss Candace. You're exactly right. So I think of all the different values of R that it can be taken on, as long as theta is equal to pi over 6. So all along this line would be things that satisfy that equation. Oh, wait. There's more. What about the negative values of R? I rotate pi over 6 and then I back up. So that line would satisfy the polar equation theta equal pi over 6. Good. Great. That's not great. Try that again. Excellent. Hey, let's try graphing some of these. Let's try graphing R is equal to pi, or sorry, 6 theta. Try that. Now, what we're going to find out, in our old graphing analysis, we'd start making a list of values that the independent variable may take on. And then we plug them into our equation and we find out the values of what we call the values the dependent variable would take on. So I've got a great idea. what happens when theta is 0? What value does r take on? Sine of r is, sorry, the sine of 0 times 6. 0. Sine of 0 is 0. So that location on our graph would be, I rotated 0 and I went away 0. Oh, that's just the origin. Now I'm going to throw out a unusual value for theta to throw out, but I've done this problem before, so I have a little insight. What happens at pi over 12? It'd be the sine of pi over 2, and the value of sine of pi over 2 is 1. So I want you to think about being on this angle, pi over 2, and going out exactly 1. And let's think about what happens in between there. We get a graph that looks kind of like this. The angle's changing, r is getting bigger, and goes out to 1. Something like that. Maybe I'll do it in red. All right. My next try is going to be at pi over 6. So that's sine of pi, which is 0. So here's the angle pi over 6, and what we're saying is we're going to go back down like that. Okay? And I'm just going to do a couple more of these. I want to do 3 pi over 12. Which would be what? 3 pi over 2. Negative pi over 2, which is negative 1. Okay, so now I'm on this particular angle, but I got a negative value. So even though I'm sweeping in the first quadrant, I end up getting a point that's down here in the third quadrant, a negative r. And it goes shoop. And then the next one I'm going to do, by the way, is going to be, I'm going to add another 1 pi over 12. I'm going to end up at pi over 2. And at pi over 2, do the same thing as 3 pi, and we're back to 0. And we go zoop. So I keep on doing that for a while until I'm bored. And then so wouldn't it be nice to have the calculator do this for me? And that's what I'm going to do. Let's go. Let's have the calculator show us what the rest of this looks like. Well, we'll deal with that. Let me get into polar coordinate mode. I mean, you guys were doing this while I was doing all that hard work. I haven't forgotten what the problem was. What is it? Sine of 6 theta. And you'll note that when we're in polar mode, our independent variable key turns into a theta. If I do zoom 7, you get this really small thing in the bottom there. I'm just going to go zoom. I'm going to choose zoom in, hit enter, enter. And that's kind of nice, but I'm going to do one little change. I'm going to make my theta step a little bit smaller, mostly because a tenth of a radian is like 6 or 7 degrees, and I want to try to make this thing a little bit more smooth. And there you see those first 2 leaves. Actually they're called petals, because the name of this particular curve is called actually no, that's not true. They call this a 12 leaf or 12 petal rose. I'm not saying it makes sense. By the way, I might choose zoom square to make this one look a little bit more symmetric. Every single time we have a turnaround, we're exactly 1 away from the origin. By the way, if we let this run even further, what ends up happening, it just ends up retracing over the same routes again. Right? And so that's one of the amazing polar graphs we can get out. Again, it's 12 leaf rows is what this is called. All right, fascinating. But maybe less fascinating is the second one. Let's take a quick look at r is equal to 1 minus 2 cos. You know what? I really don't have time to take you through the independent variable, making the t-chart thing. Let's just go to the calculator, okay? All right. Oh, yeah, I'm dragging you kicking and screaming on that one. All right. So 1 minus 2 cosine theta. And I'll just hit graph and see what we get. It seems as though we're off the viewing screen. We're only seeing a small portion of this. I think we're going to have to zoom out. How big can cosine get? Well, it can get as big as 1, and when it's as big as 1, we get 1 minus 2, so we get about a negative 1. But what about when cosine is as small as negative 1? I get 1 minus 2 times a negative 1. I can get as big as 3. It looks like the 3 stuff is getting way over there. I'm going to change my viewing window so that I'm going to go from as low as negative 3. And I'm going to do the same thing in the y coordinate. Actually, I probably should do this for my x max as well. All right, let's graph that, see what we get. So it's going around. It's kind of like a spiral. And it's got that little inner loop. I want you to notice when it graphed, it started with theta equals 0. From theta equals 0 to theta equal pi over 2, it actually drew this portion of the graph. From theta equal, so this was theta between 0 and pi over 2. Actually drew down this. And then this part, sorry, I'll do this in green. This part, it drew that when theta was from pi over 2. Wait, did it draw that one last? Yeah. Okay, so.
It went like a spiral.
Yeah, starting at didn't start there.
Where did it start?
Right.
Where it started from the x-axis.
No,
Over to
Left.
the
-1.
At negative 1?
Yeah. And then it went down.
Okay.
And all the way
And
around.
then
All the way.
up. All the way.
Yeah.
And all the way back down. Okay. The thing I want you to leave with this in this particular drawing is that certain parts of the curve correspond to certain values of theta. That's going to come up and be really important later on in the slideshow. All right, so we got one more to do. We've got one more to do, and it is r is equal to 4 sine theta. Let me put that one in real quickly. Clear 4 sine theta and graph it. Again, it seems to go off the screen. A big old oval looking thing. Well, let me think about 4 sine theta. 4 sine theta, sine gets as big as 1. So it looks like I'm going to get as high as 4. So let me change my y max to 4. In fact, I don't think I need to be anything more than -1 there. And it's kind of like a football. It's a circle?
Yeah.
How do you know? Well, by the way, it's still drawing. You see it's still drawing?
Is it retracing?
Yeah.
It's actually retracing. What went on, essentially, we started here at theta equals 0, and we got to theta equal pi over 2, and then we got to theta equal pi. Now, officially we'd be in the third quadrant, but in the third and the fourth quadrant, sine is negative. So although our theta is in the third quadrant, we're drawing with negative r's, and it goes from pi to 3 pi over 2, and then from 3 pi over 2 with negative r's again to 2 pi. So as the theta went from 0 to 2 pi, it actually traced it twice. Is this a circle? Well, what I'm going to do is I'm going to do a zoom square so that the aspect ratio looks more appropriate. Looks like a big old oval or circle? Not a circle, an ellipse. No. It's a circle. But wouldn't I have to prove that to you other than say, doesn't it look circle-like? Wouldn't it require a little bit more than just me saying?
Wait, how is it? Is it because you're, the values for the x and y values?
How about for another reason? Are you ready? You ready to go? Here we go. What do we know? We know that x is equal to cosine theta. And we know that y is equal to r sine theta. There's one other fact that I hinted at, but I didn't say explicitly earlier. That r squared is equal to, x squared plus y squared, is that right? When I draw a point and I say, hey, how far is that r? I've got two legs of a triangle, one of them x and one of them y. Yeah, that's what I have. I've got these three facts working for me. You ready? I'm going to multiply both sides by r. And I get r squared is equal to 4r sine theta. That's not too bad, is it? You're like, why am I doing this? Because it's an algebraic trick that they put in the book, and I'm just following what they did. All right, what's r squared? R squared is x squared plus y squared. What is r sine theta? It's equal to y. So I've got that equation. X squared plus y squared is equal to 4y. Oh, you know what I'm going to do? Strangely enough, I'm going to take this 4y and bring it on the other side. And I'm going to do this ancient technique in algebra called completing the square. It's an Algebra 1 technique that you should have learned about the same time that you learned the quadratic formula. I add something right here in order to make this a perfect square. The number I am going to add to make that happen is 4. Because that would make this y minus 2 quantity squared. I added a 4 to make it a perfect square. Oh wait, whatever I do to one side, I got to do the other. So let me add a 4 over there. And what do I have? That looks to me a lot like the Cartesian equation for a circle centered at 0, 2 with radius 2. A circle centered at 0, 2 with radius 2. Looks like that's a circle. I hope I have presented sufficient proof. If you're unsatisfied, too late. We got to go on. So here are the conversion formulas that I've been using to do that kind of work. Probably not a bad idea to memorize these. Disappointed yesterday. I saw my first dandelion.
There's some couple in the concept.
Yeah, there's some in the casa lawn right now. But mostly I hate them when they're in my lawn.
You're like Clint Eastwood.
Yes, if Dirty Harry Callahan was into lawn care, that'd be just like him. Or maybe his character that was from San Marino, or Gran Torino. San Marino, different. Just a different thing. All right, let's go on. We're gonna skip that. All right. So, by the way, it may not be obvious, but polar coordinates are really just a sort of special parametric situation. Let's review this idea of parametric situations. Instead of x being a function of y or y being a function of x, in the parametric thing that we introduced or reintroduced in 10.1, they said, you know what, how about x is a function of a new independent variable? Let's call it t. Hey, how about y being a function of a new independent variable? Let's call it t. And we said, here's what happens when we have this new independent variable describing the location of x and the location of y. Well, here's an idea. Most of the time that we're working in polar coordinates, r is a dependent variable and theta is the independent variable. R is a function of theta. You okay with that idea? And then we go over here and we say, you know what? X is R times cosine theta. Oh, it looks like R is a function of R and theta. But wait, most of the time when we're talking about these curves, R is a function of theta. I can go and I can take this occurrence of R and replace it with whatever function of theta that we're working with at that moment. And what do I get? X is a function of this new independent variable, call it theta. It sounds like X is acting like a parametric. What about Y? Y was R sine theta, but if R is really just some function of theta, sine is just some, or Y is just some function of theta too. So, why is this handy? Why is this handy? Well, let's say we're doing some work. Let's say we have some function R. What function R do you want to talk about? I don't know. How about that one that we just did? 4 sine theta. That's a circle. It's what? Sitting on top of the x-axis. What if I want to ask a question like, what is the slope at some point on that circle? I could treat this situation parametrically. R sine equal 4 sine theta converts to x is 4 sine theta times cosine theta. I took the value of r and replaced it where r was in my x equation. What is y? 4 sine theta, the value of r, times sine theta again. X and y are dependent upon this new independent variable, theta.
You just take the derivative of both of them.
If I take the derivative of this with respect to theta, I get 4, it's a product rule. First times the derivative of the second plus the second times the derivative of the first. Oh, ugly. 4 times cosine squared theta minus sine squared theta. Okay, I found dx d theta, which is kind of like our dx dt from section 10.1. Let's do this one. This one looks a little bit easier. This is 4 sine squared theta. So what is dy d theta in this case? 4, bring the exponent down, keep the inside the same, and then multiply by the derivative of the inside. Okay, it looks like it's 8 sine theta cosine theta. All right. Put them together, and what do you got? I'm waiting for someone to say bibbidi bobbidi boo, but no one did. All right. I'm hearing the female voices are Cinderella. Guys, like, even if I know it, I'm not admitting it. All right, so what do we end up with? We end up with an expression that you give me a theta, I can plug it into there, and I can tell you the slope, like the xy slope for that situation. It's just a special kind of parametric. Just a special kind of parametric. All right, that's enough of that nonsense. Skip that one. We got to get to this one. You're like, oh no, skip that one too. No. Because we do have to hit this last bit of calculus having to do with polar coordinates. All right? Skronsky, right?
Yeah.
All right, Skronsky. All right. Last part of this discussion has to do with the other things that we do in normal xy functions. We find areas under curves. The old metaphor was, you know what, I take a little slice of x, I multiply it by the height of a curve. Stop working on me for a second. Okay? And that delta x times f of x gives me the area of a rectangle. I say area because it could be a negative f of x and we have negative area. Now let's forget that whole discussion right now. But we get a bunch of little rectangles. And if we want to find the area underneath the curve, we add up all those rectangles. This drawing leads to the fact that the area under the curve is from A to B is f of x dx. Do you remember, can you recognize that starting point? And it led to that conclusion. But polar coordinates are different. Our independent variable now is theta. And we imagine sweeping with pieces of theta. The pieces of theta look like pie slices. And it is not true that this distance r, times delta theta is equal to the area of that pie slice. It's not true. We're going to need to do something different in order to get the area inside of a polar curve. Here's what we're going to have to do. I want to think of a circle. Here's a circle. A circle with a constant radius centered at the origin. I want to know about the area of that circle. It has radius r, by the way. Pi r squared. Oh, thank you. About freaking time. There we go. Pi r squared. Okay? But you know what? I don't want to know the area of the entire circle, really. I want to know what happens if I make a pie slice of it. I want what's called a sector area. I might ask the question, hey, how much area if it's a sector area of pi over 2 in angle? It'd be a fourth of it. So if I said something like area and the sector slice was pi over 2, you would say it's pi r squared divided by 4. Now that's correct.
It's pi over 2 divided by 2 pi.
But it's not as helpful as saying what would we get for some general slice. What do we need? What's the area for some slice that's exactly delta theta big? Okay, and you, Mateus, you said it so quickly. I want to write it down now. This is equivalent to pi r squared times pi over, or 2 pi divided, no, other way around. Sorry. Pi over 2 divided by 2 pi. The idea being here that this expression is the 1/4 that Jordan was talking about. I take the angle, and if I divide it by pi over 2, it gives me the fraction of the circle that I'm dealing with. So if I wanted for some arbitrary angle, call it delta theta, I could take this expression, pi r squared, I could drop the delta theta, that's my angle, and I could divide it by 2 pi, and now this part is that fraction of a circle that I'm dealing with. But that's ugly. Let's clean it up. Clean it up. Take the red marker and say, you know what? I've got a pi here and I've got a pi there. Get rid of them. And what I'm left with the rewrite is 1/2 r squared delta theta. Now, if we started over here with the idea that the area of the rectangle was equal to f of x times delta x, and it led us to the conclusion that the integral from a to b of f of x dx is the area under the curve. Where do you think I'm going with this? If the area of a sector that's delta theta wide is 1/2 r squared delta theta, because as the slices get thinner and thinner, the big delta thing becomes a d theta. And that's what we end up with. That's what we end up with. The area in inside of a polar curve is 1/2 r squared d theta. That is a lot. But remember, r is just a representative for the function of theta. Well, we have a tendency when we're talking about x ranging on a set of values, they range from a to b. For angles, we have a standard that the angles range on Greek letters from alpha to beta. I don't know why. As far as I'm concerned, they could range from smiley face to peace sign, and it'll be just as good.
You said something really weird. It was like
I say something weird almost every day,
mobile
Charles.
home to moose or something like that.
Moose head, I think. Not sure though. All right, so let's do a quick problem using this. I'm going to use a blank slide. You know what? I showed you this particular function. R is equal to 4 cosine. Sorry, we did sine theta, right? 4 sine theta. Can we remember what that graph looks like? It's a circle that goes like this. Okay, it has a companion curve, which is 4 cosine theta, which is also really nice to memorize. It looks like that. It starts right here when theta is 0 and cosine is 1. And as theta goes from 0 to pi over 2, it goes that part. As from pi over 2 to pi, it does that part. And it does that same cycle every pi. Let's find the area of that circle using this new technique. It might be easier to not find the area of the whole circle, but rather find the area of the half circle.
Double it.
And double it. So the area of this is twice times 1/2 r squared. But what is r? R is 4 cosine theta squared d theta. And for what range of thetas do I get half the circle? I start here at 0 and I end here at pi over 2. So let's just do it on this particular range of values from 0 to pi over 2. And then I'll double it and I'll get the area of the whole circle. Well, let's see what we got here. That 2 and that 2 cancel. That's kind of nice. When I square this, I get a 16 that I can pull out to the outside. And I get a pi over 2 cosine squared theta d theta. Do you remember how to take the antiderivative of cosine squared? Can we have like a trig identity that's really helpful here? Something like 1/2 plus 1/2 cosine 2 theta d theta. Did I ever do this with you guys? No? Oh. This is, whenever we get like a sine squared or cosine squared, there's this thing called the power reducing formula. This is equivalent to cosine squared, and there's another one which is great for sine squared. Sine squared theta is equal to 1/2 minus 1/2 cosine 2 theta. They're called the power reducing formula, so really handy. All right, let's finish this off. Now that I've done this trig identity, we can do the antiderivative pretty easily. The antiderivative of 1/2 is 1/2 theta. The antiderivative of 1/2 cosine 2 theta is 1/4 sine of 2 theta as evaluated from 0 to pi over 2. double check that for me, please. I know cosine becomes sine. If I did a u substitution, it would create an extra 1/2. Okay. All right, so what do we get? We get 16 times, if I plug this in, I get 1/2 times pi over 2, plus, when I plug this in, I get sine of 1/4 sine of pi, minus 1/2 times 0, plus 1/4 of sine of 0. Now something nice happens. Sine of 0 is 0. 1/2 times 0 is 0. Sine of pi? 0. Which leaves me 16 times pi over 4, which is 4 pi. Now is it true that a circle with radius 2 has area 4 pi? Yes, it is. All right. So here's what we're going to do. This is not your assignment. Get rid of the 1, change it to a 49, I believe is correct. And 49 through 59 on focuses only on the thing that I'm most concerned about, and that's the area problems. The area problems are the ones that are most likely to show up on the AP exam, and so I want you to give those a try. We'll see you tomorrow. 1 second, let me turn off the recording. Oh, I'm sorry.